The Kamchatka Trench just ruptured, and it has scientists sending mega tsunami alerts across the Pacific as one of Earth's most dangerous fault zones shows signs it's about to unleash hell. This vast undersea battlefront, where tectonic plates grind with monstrous pressure, triggered a magnitude 9 quake and deadly tsunami in 1952, killing thousands in minutes and sending waves across continents. Now, sensors are detecting rapid seafloor uplift, tremor swarms, and stress patterns eerily similar to that historic disaster. Only this time, everything is happening faster. Could this be the countdown to a Pacific-wide catastrophe greater than anything we've seen? The alarms are blaring. What happens next will decide the fate of coastal cities worldwide. At 14:37 local time, the first seismic pulse from the Kamchatka rupture hits the Pacific Tsunami Warning Center's mainframe. Monitors flicker with jagged lines, alarms slice through the hum of machinery, and operators snap to attention. On the internal Slack channel, a message appears. Confirmed. Main rupture. All staff to warning desks. Verify signal separation. Possible megathrust. The room is suddenly electric, every second stretching thin as analysts scramble for clarity. Phones ring in rapid succession. One operator's voice cuts through the chaos. Modeling run? Now! We need wave arrival times for Petropavlovsk and Hawaii, all channels. The supervisor, eyes locked on the evolving waveform, issues the order. Priority broadcast. Coastal cities from Kamchatka to San Francisco, now in yellow status, will escalate as more data comes. In these moments, the center's routine transforms into a race against time. Staff huddle over live maps, cross-checking automated readings with manual calculations. Some models show a massive displacement, others hesitate. There's no consensus, only the relentless tick of the clock. 6 minutes after the first alert, sirens begin to wail along the Russian coast, and cell phones trill with emergency notifications across the Pacific Rim. A PTWC operator later recalls, "You could hear people shouting for live model runs. Some stations doubled their water level readings, just like the replay films of 1952. Nobody wanted to be the one who missed the signal." In the control room, tension is a living thing. Desks are littered with printouts, coffee cups, and hastily scribbled notes. Eyes flick from one screen to the next, searching for patterns in the chaos. The warning chain is only as strong as its weakest link, and tonight, every link is under strain. Outside, the world waits for answers. But inside the warning center, every decision is measured in lives. The next few minutes will determine how many get to higher ground before the waves arrive. Beneath the surface of the Pacific, silent forces have been at work for months. Deep-sea sensors anchored along the Kamchatka Trench began logging vertical uplift as early as January. At some points, the seafloor rose by over 2 meters in a matter of weeks. Hydroacoustic arrays picked up bursts of low-frequency tremor and sudden gas venting, the kind of signals that hint at rocks grinding past each other under extreme pressure. Satellite radar, using INSAR technology, mapped a deformation zone stretching for hundreds of kilometers, with ground movement patterns that match only the most dangerous phases of megathrust loading. The numbers are stark. Uplift readings peaked at 2.1 meters in certain segments, while slow slip events, where the fault moves too gradually to trigger a quake, but still releases massive energy, ran 2 to 3 times above the decade's average. The Pacific Plate is now pushing beneath the Okhotsk Plate at almost 97 millimeters per year, making this one of the fastest subduction zones on Earth. Each millimeter is a fraction of a bomb, energy stored until the rock can't hold anymore. Dr. Alexei Petrov, stationed at a windswept outpost of the Kamchatka Volcanological Institute, describes the mood among field teams. Some seafloor deformation rates we're recording are double what we saw before the 1952 rupture. There's a real sense of urgency among the field crews. In the data, the warning is unspoken but clear. The deformation zone isn't just a line on a map. It's a vast scar stretching across the seabed, growing by centimeters day after day. Even the slow slip events, usually invisible to all but the most sensitive instruments, have become impossible to ignore. Recent hydroacoustic records captured a cluster of harmonic tremors, followed by a sudden spike in methane venting, signs that the fault is actively fracturing, not just straining. Every metric feeds into the models racing across supercomputers in Tokyo, Honolulu, and Moscow. The numbers don't lie. Physical strain is already underway, and the Kamchatka megathrust is closer to failure than at any point in living memory. The numbers coming out of the supercomputer models are staggering. The USGS finite fault solution for the July 2025 rupture reveals a peak slip of 40.3 meters, almost twice the maximum displacement seen in the infamous 1952 event. Along a 600-kilometer stretch of the fault, the crust lurched with such violence that entire sections of the seafloor shifted in a single, unstoppable motion. This isn't just a matter of magnitude. The geometry of the rupture, with its broad, shallow slip zone and abrupt tapering near the trench, means energy was transferred not just downward, but outward, priming adjacent fault segments that haven't broken in generations. Stress modeling paints a picture of a fault system on edge. After the July earthquake, Coulomb stress transfer calculations showed at least 2 major patches now sit at their critical threshold. Slow slip events and foreshock clusters have loaded these segments even further, leaving scientists with a chilling conclusion. The main rupture may have only been the opening act. Dr. Jane Hubbard, a leading USGS earthquake modeler, puts it bluntly: the intensity and sequence of these foreshocks are without precedent in our modern records for this region. It's exactly what kept us up at night after seeing preliminary data. For the first time in decades, the probability models are not offering comfort. The official USGS aftershock forecast now assigns a 4% chance of another magnitude 8 or larger earthquake in the region within the next year. That number may sound small, but in the world of seismic risk, it's a glaring red flag, an annual probability many times higher than the long-term average for such catastrophic events. Every new slip, every microquake, is a roll of the dice. The Kamchatka megathrust is not just active, it's restless, and the numbers say the threat is far from over. Sirens blare along the Kamchatka coast, but in dozens of villages, the alarms never sound. In Petropavlovsk-Kamchatsky, the latest evacuation drill showed just 48% of residents could reach high ground within the critical 30-minute window. The rest are trapped by steep roads, narrow bridges, or gridlocked intersections, bottlenecks that turn minutes into a death sentence when every second counts. Traffic simulations in Crescent City, California, paint a similar picture. Emergency planners watched as virtual cars jammed at bridge crossings, their digital avatars inching forward, while the simulated wave raced ever closer. Hospitals in the region run surge scenarios. The numbers say local emergency rooms would be overwhelmed within 2 to 3 hours of a Pacific-wide tsunami. Ambulances would be stranded behind panicked drivers, and medical staff would face impossible choices as the wounded flood in. Along the Russian coast, entire villages rely on a single siren or a town official with a megaphone. Some outlying settlements have no warning system at all. Cell networks buckle under the surge of emergency alerts, leaving families to rely on word of mouth or distant radio broadcasts. In the chaos, the gaps become brutally clear: outdated sirens, missing bridges, evacuation maps that don't match the real world. Maria Gonzalez, a NOAA emergency planner, puts it without hesitation: if we face a Pacific-wide tsunami, it's these choke points, congested highways, and outdated siren networks that will decide survival rates. The numbers are not just statistics. They are the difference between life and death, measured in the time it takes to clear a bridge or the distance to the nearest hospital. When the next wave comes, the weakest links will be exposed, and the cost will be counted in lives. Inside the Russian seismic network's headquarters, the crisis is not just geological, it's bureaucratic. A leaked memo from the Russian Academy of Sciences, dated March 2024, details a 38% budget cut to the Kamchatka region's seismic operations since 2020. Over 24 maintenance requests for critical instruments sit unresolved, some for more than a year. In the weeks before the July rupture, field teams reported outages at 3 deep ocean sensors, blind spots right where the foreshock swarm was most intense. When the main rupture hit, those sensors were still offline. Dr. Elena Ivanova, who oversees seismic network maintenance, wrote in her field notes, "We lost 2 of our best stations during the foreshocks. If the main rupture had started further west, we might not have caught the first signals in time." Her warning is echoed in a string of internal emails, engineers pleading for spare parts, supervisors requesting emergency funds, and a regional director warning that the network is operating on a shoestring with no margin for failure. The official story is one of resilience, but the documents tell a different tale. A cable dispute between federal and regional agencies stalled the upgrade of deep-sea links for over a year, leaving parts of the network reliant on aging satellite relays and manual data uploads. In the chaos of July, operators scrambled to fill the gaps with borrowed gear and improvised connections. The maintenance backlog now stands at 24 unresolved items, including a failed backup generator at the Petropavlovsk hub and a broken tide gauge near Ust-Kamchatsk. The cracks in the warning network are not just technical, they're the result of years of political choices. As the Pacific holds its breath, the question is no longer whether the science can see disaster coming, but whether anyone will listen in time. 15 minutes after the rupture, the first wave models deliver their verdict. In the simulation, a wall of water races outward from the fault, its leading edge reaching the Kamchatka coast in under 20 minutes. The numbers are brutal. At Ust-Kamchatsk, the projected run-up climbs past 17 meters. In Severo-Kurilsk, the model flashes red. Localized pockets could see water surging as high as 19 meters, swallowing the harbor and washing deep into the town's low-lying center. Not every coastline is equally doomed. The trench's jagged profile funnels energy into narrow bands, creating deadly amplification zones where the wave height can double in a matter of seconds. A fishing village perched on a headland might be spared, while a settlement tucked behind a river mouth faces obliteration. The model's clock ticks forward. 35 minutes from the rupture, the wavefront explodes across the Kuril Islands, then fans out toward Japan, Alaska, and Hawaii. In the simulation, the Pacific becomes a chessboard of risk. Crescent City, California, lights up with a projected run-up just below 2 meters, enough to breach seawalls and flood downtown streets. In Hilo, Hawaii, the first crest is modeled at 1.2 meters, but the real danger lurks in the second and third waves, amplified by the shape of Hilo Bay. The simulation pinpoints micro hotspots, places where deep undersea canyons focus the energy like a magnifying glass, sending water barreling inland far beyond what the average forecast predicts. Every minute brings a new set of numbers. In some places, the wave is expected in under an hour. In others, it will take 3, but the model offers no comfort. It's not just the height that matters, but the speed and force, enough to rip foundations from the earth and sweep away entire blocks. The run-up maps don't lie. This is destruction measured in meters, minutes, and the thin line between safety and disaster. The data is relentless, indifferent, and it doesn't care who's watching. A grandmother in Petropavlovsk, Kamchatsky, stands at her kitchen window, clutching her granddaughter's hand as the sirens wail. She remembers the stories her own parents told, how in 1952, the sea swallowed half the town before anyone could run. Now, she faces the same question. What do you do when the wave is coming and there's nowhere to go? Her words cut through the noise of statistics and simulations. We run the drills every year, but people still panic. My granddaughter asked if the big wave was coming again, like when my own parents ran from the sea. The fear is real, but so is the chance to act. Every disaster leaves survivors, and every survivor has a lesson. In Severo-Kurilsk, families rebuilt homes from the wreckage, sharing food and shelter, drawing evacuation maps on scraps of paper when official ones failed. Their voices echo across the Pacific. Preparation is not just about sirens and simulations, but about knowing your escape route, keeping emergency kits ready, and teaching children where to run when the ground shakes. Experts urge a simple roadmap. Memorize high-ground locations, keep a go bag with essentials, and never wait for a second warning. Push for transparent reporting from local authorities. Demand that siren networks and evacuation maps are kept up to date. If you live in a coastal zone, know exactly how many minutes it takes to reach safety, and practice it, not just once, but until it's muscle memory. Neighbors who check on each other during drills are the ones who save lives when the real wave comes. The science may be uncertain, but the power of community is not. The next wave is coming, whether it's next year or next decade. Survivors are not just lucky, they are prepared, persistent, and loud. Their message is clear. Don't wait for help from afar. The first step is yours. The next life saved could be your own. On November 4th, 1952, the Kamchatka Trench triggered a magnitude 9.0 earthquake and tsunami that killed over 2,300 people in minutes. Today, deep-sea sensors confirm 1.7 to 2.1 meters of seafloor uplift, and a slow slip rate up to 3 times normal, echoing the seismic patterns before that disaster. In 2025 alone, 7 earthquakes above magnitude 7 have struck, and the USGS estimates a 4% chance of an M8+ event within a year. Yet, the exact timing and scale of the next rupture remain unknown. Critical seismic data and some government records are still classified. Despite decades of research, the Kamchatka megathrust continues to defy full prediction. The evidence is clear. The fault is building toward another massive release, and coastal cities across the Pacific remain at risk. As history has shown, nature provides warnings, but it is up to us to act before the next wave arrives. Mount Etna eruption shocks. Geologists. What came out has never been seen before. Bright, glowing rock poured from the crater, defying centuries of geological records. Not basalt, not andesite. Its composition is so strange that 3 top European labs have failed to identify it. At the same time, Etna's slopes unleashed a pyroclastic flow, and seismic readings hint its deep structure is shifting, echoing conditions before the catastrophic collapse that triggered a prehistoric tsunami. If this isn't a warning, what is Etna trying to tell us? And what happens next? Mount Etna's restlessness is legendary, even among volcanoes. For more than 3,500 years, this mountain has rarely slept. Historic records and ancient chronicles agree. Eruptions are not the exception, they are the rule. On average, Etna erupts in some form more than 8 out of every 10 years. That's a higher frequency than almost any other major volcano on the planet. In the past century alone, over 60 eruptive episodes have been logged, some lasting mere hours, others stretching for months. The 2001 and 2002 events, for example, sent lava and ash across the Sicilian countryside, forcing evacuations and grounding flights. But even those dramatic moments are just the latest in a long chain. Archaeologists have traced layers of ash and lava back through Roman times, and even further, to Bronze Age settlements buried beneath black rock. Each layer is a timestamp, marking yet another burst of energy from deep inside the earth. Paroxysms, those violent, short-lived eruptions, have become almost routine here, with more than 50 recorded since the early 20th century. Etna's activity isn't just a spectacle, it's a relentless process that shapes the land, feeds the soil, and disrupts the lives of everyone living in its shadow. The volcano's constant output means that new craters, cones, and lava fields appear with startling regularity. In some years, the summit changes shape multiple times. Vents open, close, and shift position, as if the mountain itself is breathing. This long, unbroken record of eruptions sets Etna apart. It's not just a volcano that erupts. It's a volcano that almost never stops. That unyielding activity, is the surface signature of something far more complex happening beneath the ground, a hidden blueprint of chambers, conduits, and shifting faults that scientists are only beginning to map. Deep beneath Mount Etna, the story of every eruption begins in a hidden world of molten rock and shifting pressure.